Well, maybe wrong is a bit of a stretch. But is everything about Einstein's theory right? Let's dig a little deeper into his theory and take a closer look with a different perspective on today's new technology. Even though the general relativity theory proposed by Albert Einstein has achieved remarkable success in describing the gravity of stars and planets, however, it does not appear to work perfectly across all scales. So, is Albert Einstein's theory correct in every way? Gravity exists everywhere in the universe and is felt by everything. However, physicists face the greatest difficulties with this fundamental force, which is also the most prevalent of all of them. Although the general relativity theory proposed by Albert Einstein has demonstrated remarkable success in describing the gravity of stars and planets, it does not appear to hold up across all scales. From Eddington's measurement of the deflection of starlight by the Sun in 1919 to the recent discovery of gravitational waves, observational tests of general relativity have been conducted for many years. However, when we attempt to apply it to extremely small distances, where quantum mechanics laws operate, or when we attempt to describe the entire universe, we begin to notice gaps in our understanding. Einstein's theory has now been tested on the largest scale yet in our new study, which has been published in Nature Astronomy. The results suggest that the general relativity theory may need to be modified on this scale, and we believe our method may one day help resolve some of the most significant cosmological mysteries. According to quantum theory, there is a lot of energy in space or the vacuum. Because our devices can only measure changes in energy rather than their total amount, its presence is invisible to us. However, Einstein asserts that the energy in the vacuum has a repulsive gravity that pulls the space apart. It is interesting to note that it was discovered in 1998 that the universe's expansion is accelerating, a finding that was recognized with the Physics Nobel Prize in 2011. However, in contrast to what quantum theory predicts, the amount of vacuum energy, or dark energy, that is required to explain the acceleration is much smaller. The big question, also known as the old cosmological constant problem, is therefore whether the vacuum energy gravitates, thereby altering the universe's expansion. If this is the case, then why is its gravity significantly weaker than anticipated? What is causing cosmic acceleration if the vacuum has no gravitational pull at all? To explain the expansion of the universe, we must assume the existence of dark energy, even though we do not know what it is. In a similar vein, to comprehend how galaxies and clusters have developed into what they are today, we must also assume that some kind of invisible matter known as dark matter exists. The lambda-cold dark matter, LCDM, model, which holds that there is 70% dark energy, 25% dark matter, and 5% ordinary matter in the universe, is based on these presumptions. Additionally, this model has been remarkably successful in fitting all of the cosmological data gathered over the past 2 decades. But many physicists have wondered if Einstein's theory of gravity needs to be changed to describe the entire universe because the majority of it is made up of dark forces and substances that have strange values. Another curve seemed a couple of years prior when it became obvious that various approaches to estimating the pace of vast development, named the Hubble consistent, offer various responses, an issue known as the Hubble strain. There is tension, or disagreement, between two Hubble constant values. One is the number that is predicted by the LCDM cosmological model, which was created to match the cosmic microwave background radiation, light left over from the Big Bang. The other is the rate of expansion that can be determined by looking at supernovas, exploding stars, in faraway galaxies. The Hubble tension can be explained by modifying LCDM in a variety of theoretical ways. Alternative theories of gravity are one of them. Looking for answers, we can design tests to determine whether Einstein's theory applies to the universe. According to the theory of general relativity, gravity is the bending or warping of space and time, affecting the paths that matter and light take. Importantly, It predicts that gravity will bend the trajectories of light rays and matter in the same way. We test the fundamental principles of general relativity with a team of cosmologists. We also looked into whether changing Einstein's theory could help solve some unresolved cosmological issues, like the Hubble tension. We set out to investigate three aspects of general relativity simultaneously for the first time to determine whether it holds at large scales. The universe's expansion, the effects of gravity on light, and the effects of gravity on the matter were all included in this category. We reconstructed the gravity of the universe through cosmic history in a computer model based on these three parameters by employing a statistical technique known as the Bayesian inference. The Planck satellite's cosmic microwave background data, supernova catalogs, and observations of the shapes and distribution of distant galaxies made by the SDSS and DAY telescopes allowed us to estimate the parameters. The LCDM models, essentially Einstein's prediction, was then compared to our reconstruction. Even though they lacked statistical significance, we discovered intriguing hints of a possible contradiction with Einstein's prediction. This truly intends that there is by a likelihood that gravity works distinctively for huge scopes, and that the hypothesis of general relativity might be changed. In addition, our investigation revealed that merely altering the gravity theory is insufficient to resolve the Hubble tension issue. A new component in the cosmological model that existed before the time when protons and electrons first combined to form hydrogen just after the Big Bang, such as a unique form of dark matter, an early type of dark energy, or primordial magnetic fields, would probably be required for the full solution. Alternatively, the data may contain an unidentified systematic error. However, our research has shown that observational data can be used to test the validity of general relativity over cosmological distances. In a few years, we will have a lot more data from new probes, even though we haven't solved the Hubble problem yet. This indicates that we will be able to utilize these statistical techniques to continue tinkering with general relativity, examining the limits of modifications, and paving the way for the solution of some unresolved cosmological issues. Well, that's it for today. If you enjoyed the video, please hit the like button. If you have any suggestions, leave them in the comments section. And if you enjoy our content, and never want to miss a video, hit the subscribe button. Thank you for watching.